There's this famous saying, rumors of my untimely demise have been greatly exaggerated. Yeah, it's probably along this line. As you can tell now, I didn't die, but I caught a cold, a really nasty one, and I was sounding like a Wookiee in a voice break. If you want to take a peek how I sound, over at Learn Electronics Repair, Richard's channel, we did a video about reverse PCB design, and I came in for the second part, and I had this nasty pain in my throat. It wasn't fun to record. Well, it was fun to record because of Richard, but it really hurt. And after that, my voice was completely gone. So sorry for not posting videos for 4 days now, I think. As you can tell, my voice has greatly recovered. Well, enough about me. Let's go and do some electronics. And by electronics, of course, I mean, let's do some more traffic lights. Yeah, I know. How many episodes are left? I think about 2, 3, maybe. I don't know yet. When you're doing programming, you know that there's always something to do, something to optimize. So I could keep going here for a long time. I won't do that. I won't stress this. We're nearly done. And I promise after that, there are other projects waiting in the pipe that you probably really like. So in the last episode, if I remember correctly, we did things here with the traffic light sequencer. Now we have a array that tells us the ample phases over here, and these are all called in this fancy schmancy traffic light sequencer thingamajig, where we call all this horrible, this is so unreadable. Yep. It's C++. I never said C++ was great to read, and in fact, I don't see a upside if I put in many spaces, because it doesn't make it any better in my eyes. If it works for you, please be my guest, do whatever you like. Not working for me. Let's try to imagine that we are the CPU and we're running through this program. So we'll run through setup, do some initializing over here, and then in the loop, we only call traffic light sequencer. So this whole shebang is all the CPU does. And from this whole shebang, the main thing the CPU does is this: delay. It doesn't do anything else. It simply sits there and waits. The CPU does nothing productive. Let me say that again. If you only need this function, just one traffic light from this CPU, you're absolutely fine. You're done. This is perfect. The downside is, while the delay function is running over here, the CPU can't do anything else. Well, let's not go into interrupts. Let's keep it in a normal loop and say the CPU can't do anything else here. But you have there this shiny new Nano lying around that has lots and lots of pins who do nothing. You maybe want to have a second traffic light, a third one, a fourth one, and they're maybe not on the same synchronization in here. So what to do? So we have to find a way to program our traffic lights sequencer in a way that doesn't use a delay, that simply sets the LEDs and gets out of there and gives the CPU time to do anything else. All right, let's try to write this. I'll switch over to WalkMe now, because I think it's easier to explain in a clean environment what I'm going to do, because looks very crowded already. So follow me there. All right, we're back in WalkMe here, and you see I don't have anything prepared over here. There are no LEDs in here. I will use the LED built-in variable. This is D13, I think, for a Nano. But it will work on any CPU out there, because the LED built-in variable is set by the board's definition. I whipped up this small framework so we have something to start from. We are going to have an interval over here. This is a placeholder like our delay time for the traffic lights. I'll keep it simple here and only set one variable. I could use a constant for that one here, but I want to keep it simple here. So we have a interval 500 over here, 500 milliseconds in this case. In setup, we don't do anything. We do set pin mode and set it to out. We set the LED built into output so it can blink. Now I can close this now. And in loop, we do nothing more than async blink. And async blink, I prepared over here. This is this function over here. So there will be our blinking in there. We'll only blink the LED. This is way enough for us to show how we do in the delay without the delay. If we have an interval over here, we have to have a way to keep track on how many time has expired since the function has run the last time. So we probably need some way to store this, and there's a really helpful thing on board on every Nano, every Uno, every ESP something, and this is a millis function. This simply keeps track on how many milliseconds have expired since the CPU started. In fact, there's a same thing with microseconds, but these are numbers that are way too big. Precision-wise, this is way more than we need. So let's keep a variable in here and call it last time. This is the last time the function had run. So to initialize the variable, set it to 0. And since it's a timer variable, we probably need an uint32 type. Now we're into a problem. Every time we call this function, what will happen? This thing will run, and every time we call the function, last time will be set to 0. This is not what we want. We want to keep the value updated even after we leave the function. Well, there are two ways to do this. One way would be to grab this last time thing and put it outside the function, like this. I have to remove this. That makes last time a global variable. You want to avoid global variables because global address space is always precious. So you want to keep your variables inside your function somehow. And of course, it's C++, there's a way to do that. If you put the word static in front of your variable, it does exactly what we want to know. The first time this function is called, the variable last time will be initialized with a 0. And this will never happen again. This will only happen one time when the function is called the first time. After that, last time always keeps its last value. Let's try to find out when it's time to run the thing we want to run asynchronously in here. Of course, it's an if. And yeah, I do this all the time. I always write my brackets first and then fill them up, because that way I can't forget to close a bracket, or it's harder to forget to close a bracket. So if I go and say we have the millis keeps track on how long the CPU is running, and we subtract the last time variable from that, minus last time, and then we compare this with the interval. So what does this thing do? As long as millis minus last time is smaller than interval, we want to get out of here. This is my way to write it. You always can use a bigger over here, but then you have to put all the functions into the if, and this way I can go for a simple return. So as long as interval isn't reached, 500, you remember? I leave the function alone and let the CPU do whatever CPUs do when they do nothing. So what happens when interval is reached? Of course, the first thing I have to do, I have to set the last time variable. Let me get this over here. to millis. If I don't do that, the CPU doesn't know when it was the last time this function did run. And remember, it's a static variable. So this line runs only at the beginning of the program. The only time when we update last time now is over here. And of course I want to do something, so I go for digital write. And I want to go for LED built in. Let me copy that. I'm too lazy to write this again. Not digital read. LED built in. This is the whole function I want to write. You see, this is a cheap way to do a blink without reading the thing. I'll do the read and the write in one line. Yeah, I'm lazy. You know that. So yeah, let's try if this works. And of course it does. So it does blink and we don't use any delays in here. So let us again imagine what the CPU does while all the stuff here runs. We come from the setup, drop into loop and call async blink. Async blink over here asks, is our time already up? No, it isn't. We return here, and return simply ends the function, so we go back to async blink. Async blink is the loop, starts over here again, and does all the stuff over here again and again and again and again, probably 10,000 or more times a second. If our interval time is reached, we don't return here, we go into the next step that sets last time to the current millis, and then simply blinks our LED. This is the easiest way to show that there's something happening. This is how you do async stuff. Stop thinking about the loop as, oh, I have to put a lot of work in here. Start to think about the loop more like a scheduler. All the functions you want to put in there have, in fact, a construct like this at their start, so you know when they want to do something. I know there are pretty nifty libraries out there. I played around with a scheduler that even works on an Uno. So, yeah, there are pretty nice things out there. Yeah, it's nice to use those things, but sometimes it's also nice to know what's going on in there, because these are the basics of cooperative multitasking. One downside here is if you put something into your function that takes a lot of time, all the other functions won't run in this time. So you have to find ways to split your functions that they don't block the other functions. That's the main thing about cooperative multitasking. What a horrible word. Before we go back to our original program, to our traffic lights, there's one more variable in there that I want to address. Our traffic light sequencer currently uses a for loop. I marked it over here. And we need this because we have these arrays over here. The arrays need a pointer. We can say, use the 0 one, the first one, the second one, the third one, and loop this back again. So we need a nifty way to do this in here. I'm going back to the simulator right now because it's, again, easier to explain there. So I created a new variable over here and called it pointer because it's a pointer. We won't use the pointer as a pointer. We will only check, does it count up and does it wrap around at the right place? So bear with me. To keep track at what value pointers there's, I simply drop in some serial print statements in here. Let me do some serial begin over here. And the baud rate doesn't count in a simulator. And let me drop over here some serial dot print line feet and that shows pointer. Let's compile this and see what happens. And of course it stays 0 because we don't increment this. Let's do this. I can do this here, say pointer plus plus. You know, this is shorthand. I also could write pointer plus 1. That's the same. This is simply a shorthand for that. Let's compile this and see what happens. And of course it counts, and it keeps counting, and it keeps counting way beyond our arrays, so this won't fly. We need something to stop pointer from running over, say, 3, because we only have 4 elements in our array, and our arrays, remember this, start at 0. So we have to say something like, if pointer bigger than 3, pointer equals 0. Let's see if this works. Yeah, and it does work. So this would be a way to do that. You know me, sometimes I'm a stickler for these nifty solutions here, and you can get rid of the if function over here. If you don't want to get into this is just for kicks and giggles, but I love the other solution that's available for that. You simply could say, let me show you that. Pointer equals pointer plus 1 modulo 4. What the heck is a modulo? Let me show you that it works, because you probably want to know this first. 3, 0. Yeah, this is the more elegant way in my book to write stuff like that, because the modulo function over here simply divides the pointer by 4 and leaves the rest in the variable. So every time it runs over 4, there's no rest in here, because and pointer can never get beyond 3. This is not possible. So this would be my nifty solutions. Don't tell anybody. So all right, everybody, enough of these simulated stuff over here. Let's go to real hardware. Yeah, I give you that. This is a lot to take in, because if you've never written stuff like that, that's hard to get your head around. The upside is I have to write this now again, so I'll try to explain while I'm writing this why I'm doing stuff like that. So this was our old sequencer here. This is the one with a delay inside. And we're doing a new one here and calling this void, say, Traffic Lights Sequencer, I think. We know we have to keep track of time, so we need a last time variable. So static it is, uint32 type, and let's call it last time, and equals 0, just to initialize. We need a pointer to address our spaces in the array. So let's go for static, and this could be a uint8 type, and let's call it pointer. Pointer sounds nice, right? And let's keep it at 0 too. Now we have to decide, should the function run or should we leave? So let's go for the if, and the symbol calls like millis minus last time. And let me put this in brackets because I'm not sure if this could go wrong somewhere on the line. So, and of course I do this way around, and now I have to steal the delay function, the delay thing over here. This is this construct. You remember I did this with the interval, but since we now have different times in here, we have to do this way around. And this isn't the pointer we're using right now because this came from the for next loop. So there's a pointer in here now. Yeah. And if this is not a set, we simply return and leave the function alone. Last time has to be updated, because now we know, oh, the function did run. And for the next time, we have to prime the function for the next time. So we have to load last time with the current millis when the function did run. Here comes the nifty modulo part. I simply go for pointer equals pointer plus 1. And before you ask, yeah, you could write plus pointer, but I think I'd do this in a further episode where you go for more shorthand stuff. Let's keep it there. And modulo, please, 4. So this can never go beyond 3. From here on, it gets easier, because now we can simply steal these 3 and replace and what I'm doing there, and replace the traffic light state pointer with simply pointer. In one of the earlier episodes, I talked about how long should variable labels be. So I think I could relate to this because pointer is pretty clear that it's inside the structure, inside this function. And since pointer is a good name for what does it do, I think that will do. All right. Let's grab the function name. Move down to loop. Come on, my friends. Show me your loop. Drop it in here and simply remove this one. All right, let's compile and see what happens. And will you look at this? I know, function-wise, we didn't gain anything. This is still the same old traffic light we started, I think, 5 episodes ago. It still does the same. What we now have, we have a CPU that runs all its functions asynchronous. Well, it's one function. If you want to do something else on the CPU, you now can do this. There is no delay in here that blocks the execution of your code. If you want to do something else, say a second traffic light on different pins, you can do this with different timings. If you want to say control the lights of some model buildings, you can do this. if you want to check the temperature of your flux compensator, now you can do this. Well, you don't have a flux compensator? All right, we have to talk about this. Maybe in the next episode. This was more a esoterical, theoretical episode, but you see where I want to go with this. We're going to introduce more programming techniques here, and I try to give you a real-world example with that. I don't try to tell you, well, simply delays are bad and let you sit there with that, because why are delays bad? What the heck? Delay is in there, so someone sat down and wrote the code for a delay function. So let's rephrase this. Delays are sometimes bad. All right, this is it for me for today. Hope you had fun. Hope you're still enjoying this really, really never-ending series of traffic lights videos. I promise this will come to an end. And I see you in the next one, guys. Keep hacking.